Okay, so last time we covered a lot of the ideas basically about this trade-off between figuring out how to collect data, certain types of data, not very hard to collect, but they don't provide an awesome amount of coverage or, thank you, uh, like obviously good signal without any kind of data or dynamics mismatch between what is collected. Oh. And after maybe some people were thinking through that whole lecture, this is all great. It'd be really nice if we could automate this whole process so no one actually has to do any physical, I don't know, understanding of how other robotics work and be able to collect data. So that's really what we're going to get into a lot today. This is one of the first examples where basically, like, it's not easy to be able to automate the data collection process on a robot. There's always a bunch of really weird corner cases. Like if the plan was to try and collect data for a robot that's manipulating objects. Okay, if that robot drops that object, what do? You're probably, in most cases, some people are being paid to effectively babysit the robot, and then it'll go and grab that object, put it back in the robot's hand. So that's really kind of starts to start to get us to consider what types of problems are both easier to automate, and maybe that's a nicer way to be able to bootstrap data. And basically, where all these corner cases where it's really hard to automate certain things. So at least in this piece of work, because certain tasks like grasping stuff can be a bit of a problem, but here, what we can start with is basically put the robot on the ground. The idea is, in this case, the task for the robot is to clean a room. And this particular task is kind of well designed because there's not a lot of things that a human will need to intervene in order for it to be able to recover. And here, in this case, like the robot is basically trained, and the reward it gets is to pick up an object. Literally, like the sensor for the gripper on the hand will reach down, try and grasp something, lift its hand up, and if it can't close its hand all the way, there's probably at least something stuck there. And that is also a nice, good, clean reward signal for it to be able to learn from compared to all the other things that are available. So we don't have to like train an additional model to identify whether or not the agent has actually grasped the object clearly. We don't want to introduce any more, I'll say, work in order to set up this automation process. And then here, at least in this data collection process, so the agent here is just like a robot, travels around in a small room, collects and picks up a bunch of different objects. It has technically two policies, sorry, one for being able to navigate around and the other one for grasping. They both receive the same reward. So basically, it's almost like the navigation policy is rewarded for the success of the arm being able to grasp things correctly. And then from this, to add a little bit more diversity, because remember, our machine learning models like more IID data. After the agent is able to pick something up, it can just drive around randomly inside of this room and then kind of like start over again. So if you remember like a bit of this from homework assignment 1, like the agent needed to reset at the beginning of each episode. So this kind of provides a little bit of the structure. And well, rewards, we haven't gotten that far yet. We've mostly been doing behavior cloning. And this ends up working well. And by well here, the goal we're trying to get to is be able to like the agent collects the most amount of data with the smallest amount of intervention from people. So when we managed to like get this set up and finally training, the only real intervention we had to do is we had to replace the batteries on this about every 5 hours or so, and then it would eventually run out of, some battery time after that. Besides that, you could take this robotic system, put it down in any pretty much random room, and it'll learn to navigate across that room, clean up all the objects in that room. And okay, good. And then you can see a little bit more about how this works. This is a little bit better for the design. So here, this is entirely trained from scratch autonomously, and then in about 48 hours, it can go from wandering around this room entirely randomly to being able to pretty purposefully pick up every single object inside the room within about 3 minutes. The room is not enormous, but it doesn't take too long to pick up things. And then for always added effect, especially when you're doing robotics, you should put a clock somewhere in the video so it seems even more realistic and real time, so you can get a better estimate of how fast things are learning. We were also able to like add distractors to the side of the room, so these carpets that kind of interfere with objects. Maybe a bit hard to tell, but this is also random objects. These are all different colors. The internet is a great place to order lots of child's toys, essentially, in order to get robots to be able to grasp them, which is also a good thing to start with because child's toys are specifically designed to be easy to grasp and fit inside a child's hand. So we'll worry about complex manipulation later. Let's at least see if we can automate the data collection and learning process. Um, yeah, and then basically the reason why this is good is the idea is like machine learning should always eventually do a little bit better. So here we spent about 2 weeks putting together our best scripted version of this policy. We can make like a blob detector to detect objects, and then basically have the robot drive towards wherever the blob is just by computing like a delta angle. That can work surprisingly well. But the recipe for machine learning is always, okay, if you can get this to work and automate it, it can always scale better. It's like just give it more time and basically it should do better than, any somewhat expertly crafted student. So there's like 4 PhD students trying to work together to make a good scripted controller, even after that amount of time, and a lot of headache trying to figure out how to calibrate that controller well enough. We only really managed to get it to about like 60% success. So 60% is, I think within 10 minutes, it would pick up 60% of the objects in the room. And after that, it kind of run out of time. Okay. Does that make sense? Any questions? This is basically what the robot gets to see. It just had a camera mounted there on the top and gets to see a little bit of what's in front of it. So this is even a very partially observed problem, but the agent is still able to like locate objects pretty well eventually and be able to locate them and seek them out. Great. Any questions? All makes total sense. Sounds really simple. No, I mean, we're going to have 5 lectures now on reinforcement learning because this is really far from simple. As much as like the setup and design, there's like kind of like 10 years of expertise going into like which algorithm to pick specifically, which deep neural network to use specifically, what type of I guess, sampling process or exploration process to use, how to get two policies to learn at the same time, how to design the reward function. So everything about this particular paper is like capturing kind of like the essence of this entire class. But every one of those kind of pieces now, we're basically, we've covered chunks of this and we'll cover now a bit more of the RL aspect. Good question. All right. All right, great. How do we get back? Fantastic. All right, there's also the like extension to this that Google did where they had the larger robots being able to like automate and scale deep RL methods to go around and collect garbage and sort garbage basically throughout what is mostly, I think, the Mountain View office space. So this, I don't know, garbage collection seems to be a great place to scale and apply robotics. So there's not too many things you worry about breaking because it's already garbage. And it's kind of easy to understand whether or not an object is garbage or not. So it's not too difficult to make a reward. Okay. I did want to cover one thing though, real quick before jumping into RL. And this is sort of just if anyone has any questions. Well, that was about the worst thing that could happen. If anyone has any questions about the homework assignment. So I did put together, which I think works pretty well now, which is the Google Colab example. And at least there's a little bit of code here for being able to collect like some of the data from this data set. So sure, there's a bunch of stuff for installing everything, takes a little while. Make sure you go up here and select one of the other runtimes, not the CPU one, because then it won't render stuff properly in simple environment. It's at least got to pick one of these two, or if you've got a pro membership or whatever for Colab or Lightning AI, just pick something that at least has some kind of GPU. And then this is basically, I already created a data set for everybody for the homework assignment, but if you're more interested and for one of the later questions, the data set's actually used as something, it's called like an RLDS format, but it's basically stored online. Short story is this data set is probably way too big to fit on anybody's computer in this room. It's about, I think now it's actually about 15 terabytes just for the data that's currently in there. And we keep sticking more stuff into it every couple of months, so it's not getting smaller. So this just uses an interesting like function call where it's going to grab the very first trajectory from the bridge data set, which is a slightly older data set, but it at least fits on the actual computer. And in this case, it's only scaled to 256 by 256, so you can actually display and see stuff. And if this all works properly, you should get a somewhat ugly looking sketchy video here that has a couple of stops. And this is just like an example of one of the trajectories that's in the data. So this is what's going to be fed into the policy that we end up training. And then the second part here just basically displays the actions. And this is what we're going to be training that policy to then output for each of those states. And this is just, remember the output for the data set is going to be like end effector, pose, and rotation. So this should be, that's the first couple of dimensions. So this is the pose for where the hand is. In this case, it might actually look like delta pose. So it's like how much the hand changes with respect to where the current image actually is. But that's not so super important. Okay. Does that make sense so far? Any questions? No? Okay, good. At least the one thing to watch out for is in the code already, there's a bit that's going to figure out basically a bunch of scaling standardization coefficients for what's going to be used to effectively like normalize or standardize the outputs for the network with respect to this data set. Be really careful with those. If you change them too much, nothing will work at all. The loss will basically shoot off into infinity. It'll go insane. So just, I've also in the config file given some of these coefficients already, use those. If you end up trying to make up your own, just be very careful. And then the one thing that was always kind of challenging is one of the action dimensions is open or closed, which is like 100 orders of magnitude larger than all the other dimensions. Sometimes that one causes trouble with learning. So I tend to like standardize that one even more, like make it even smaller, just so it doesn't consume like most of the loss when we're doing mean squared error. And then like one feature is 98% of the error, then everything else is just kind of ignored. So there's a couple of papers actually like this. And if you look into like the OpenX data set and a few other papers, or like the code base for Octo, which you're welcome to look into, it's all written in JAX. So don't worry, there's definitely some things you will learn, but you still have to translate it into PyTorch for the homework assignment. But they do have some settings for like the standardization for the action space. You could potentially try some of those as well. But just remember the homework assignment anyway is not to do perfect on this stuff. I mean, no one has got a perfect score in terms of success on these simulators. It's just to get this stuff to learn. And I shared, the results I got from training my model, which I get kind of like an okay amount of reward. I'm sure it'd be better if I increase my data set size significantly, but then it'll never fit on my GPU. So keep that in mind. Yeah, the rest of this stuff, we're going to kind of do evaluation is actually using this simulator called Simpler Environment. I think is ironically named Simpler Environment because it's extremely complicated and doesn't install very easily and also does off-screen rendering. But it at least has a couple of tasks already encoded into it, and I managed to hack up a reward function that we can use as a measurement for like how close the hand in the simulator is to the object that it's supposed to grasp. And basically if you train the model pretty well, it'll at least start to get like the average behavior and be kind of close to the objects that it should manipulate. Okay. Any other questions about the homework assignment? At least yet? That's good. Okay. Feel free to like always ask more stuff on Discord. We'll see how it goes. But this is good to get used to. Like if you're making a foundational model for robotics, get used to using this dataset format, understanding how to use it, training a transformer. And we like transformers, especially in this case, because they're multimodal models. So we can give them images and text. Most other models don't handle different types of data very well. So there'll be plenty of work to do in the future to get them to handle these even better. Okay. Great. So if there's no more questions there, let's talk about RL. All right, and we will pretend from now like we haven't actually talked about RL as much as we've maybe like vaguely connected to it. We haven't really gotten down into any of the details. So specifically, we're going to start with policy gradients and then get into even more complicated RL algorithms. And we're going to talk a lot in this about we're going to talk about basically how to deal with and scale these algorithms. Because as much as the math sounds nice, basically whenever we take the wonderful math that is for RL and seems pretty good and solid, and then combine it with deep learning, basically nothing should work, but it magically does work because of a lot of other things that we do to kind of like prepare the network and do things like what I was just talking about for the transformer policy, like normalizing the outputs and the distribution very carefully in order to get our statistics to be safe. Okay. But these have had like success on a number of different types of problems, and then we'll kind of build up on algorithms in order to be able to do some of these. So some people might be familiar with the OpenAI 5 team, where it's basically a fair bit of engineering, but also just using a policy gradient algorithm. And I think batches of around 1 million in order to be able to train that policy. So it can make slow incremental steps on being able to do things and improve and eventually become like expert level at OpenAI, sorry, at Dota 2. There's also the other example of some of you also read about the paper for Alpha Star from Google, where they're basically training an agent to be able to play StarCraft 2, I think in this case, not the original version. And this also used its own slightly different set of methods in order to be able to train well. And last one, this is that example I was just mentioning about where there's been a couple of pieces of work that just like using deep RL at scale, this time more so on robotics, in order to be able to like clean up the garbage around the office. I guess I don't know. I suppose the people that work in the Mountain View office at Google don't have any time to sort their own garbage. So instead of doing that themselves, they decided to make a whole research project that I think took about 18 months to collect enough data, give or take. So you're welcome to go read a couple of these. Obviously, there's some examples. There's certainly a lot of details in there about like how to get these algorithms scaling a bit better. Um, and more so, I think in the next lecture, I'll cover some stuff related to RL for RLHF. It's called the from human feedback, it's vaguely reinforcement learning, but I won't get into that right now until we know RL well enough. But there's also been a lot of successes for applying RL for robotics. The most obvious one is basically any sim to real, where we can just use RL to basically learn a policy in a simulation and then apply that onto the robot. So then we don't actually have to figure out how to encode like the reward function in the real world, which could be really hard in many cases. And yeah, there's a couple of these papers that do actually do the training in the real world, but that is often only easy when it's not difficult to be able to encode the reward function, or it can be extremely deterministic and not problematic. And then if you want, you're welcome to go check up this GitHub repo. This is where at least I keep a somewhat short list of all of the reinforcement learning applications, what I call like in the wild. So this is like, it's not one of my research projects, but it's a company actually showing like this is how we use RL for business purposes right now. It's actually quite a growing list these days. But there's a lot of other examples using RL to be able to control nuclear fusion. It's been used a lot for like power consumption and control for different types of things lately, or for water treatment from a couple of my colleagues at U of A. So it's RL is really taking off in the last couple of years. It's kind of like reaching that maturity level where there's not as much hyperparameter tuning that needs to be done. And it, at least from a base level, like algorithms, the algorithm can be applied to some problem and be at least a little bit better than whatever expert controller already existed. So it's gaining a lot more popularity despite it being used a lot for RLHF lately as well. Okay. All right. So now starts the journey for us to figure out how to actually get this far and get these algorithms working. All right. So we all remember our favorite basically distribution over trajectories. Okay, but now in this case, we don't know what the dynamics is going to be. We don't know the initial state distribution. And we're doing model free RL here, which means we're also not going to try to explicitly model these at all. So there's no more like learning a Ford dynamics model. We're just going to directly optimize a reward function to find a policy that's supposed to be like optimal on that reward function. Still same objective. So nothing new here. In fact, like even less than what we've talked about so far. Let's do this with fewer models. All right. So then a little bit on this like first version of talking about reinforcement learning. So hopefully everyone recognizes this function. So this is just maximum likelihood. You've got, your x's as inputs, your y's that are labels. You want your model to basically produce the proper output for that particular y, or in this case, like an action. So there's no rewards up here on the top. And one way to think about now the way we're going to end up applying reinforcement learning, at least for policy gradients, is actually just kind of a small change to this. We're no longer, the agent isn't going to have like direct labels of this is the expert thing to do at this particular spot. It's only got a reward function. So basically just take this like exact objective and then just add on to the end of this. Okay, there aren't targets, or essentially the target here is going to be now weighted by a score function that just says, okay, now adjust this according to this likelihood. So before this was essentially just 1 for maximum likelihood, and now this is at least going to be some weight where some actions are going to get, either a value closer to 1 or closer to 0, depending on how you want to think about this. And that's all this process essentially is, although we're going to get into some more of the details about how to approximate this better. And then you can kind of see the visualized version of this over here, where if there's a couple of trajectories, the trajectory that got the highest reward is then going to have the largest weight here on the right for this function. So it's more likely that the probability distribution will be shifted towards those higher value trajectories. And that's it. That's like reinforcement learning in one page. That's just basically like trial and error. Trial, run a trajectory, have some error, use it to adjust your loss and your model a little bit. Okay. Does that make sense? Any questions? Okay. So this is the nice basic conceptual version. And now there are tons and tons of research papers to try to get this to be easier to apply and work, for larger types of problems. But the first thing to start with is just to think a little bit about policy distributions. So there's different ways that, you can basically model the probability distribution for a policy. There's really been like 2 primary ways of doing this that have been used a lot. So if you go and load up something like the CleanRL library or some version, you'll normally get basically these 2 options. One is just basically, sorry about that. One is just basically cross-entropy. So in this case, the policy in the action space is discrete. So we're just learning essentially classification and trying to adjust this distribution to have like, in this case, less cross-entropy wherever the advantage here is higher. So whenever you see like something that's going to be discrete actions, this is the probability distribution that's most often used there. And then whenever there's continuous actions, it's basically a Gaussian distribution. And that's how we'll represent that probability or basically likelihood for any of the actions and the data set that it's being adjusted for. And this is just as an example from this, if you're modeling some policy as some Gaussian distribution, many papers do this in a slightly different way, but basically this is the mean. Sometimes the variance for the policy is learned, sometimes it's not. Really depends on the paper. You have to dig into the details to see the actual difference. But if the covariance is basically always something that's fixed, then essentially, you could just do mean squared error on the mean that's coming up for this individual policy, and that's how you'll end up like minimizing the loss for the outputs of the network. Nothing super complicated yet. Okay, does that make sense? So this, as much as these things are just math, somehow you have to compute like a likelihood given some distribution for this actually in your code. It's usually like something like a cross-entropy distribution or a Gaussian distribution. All right. This is also kind of what you're doing almost exactly for homework too, because one of the questions is basically use a cross entropy like a discretized distribution versus using a Gaussian distribution. See which one works better. Because you can always discretize a continuous distribution into some number of bins. And that can be nice, especially if your distribution is very multimodal, because Gaussian distributions do not capture modes very well. And we've talked about how data that is collected from people tends to be a bit more multimodal, somewhat annoyingly. Okay. All right. So then how about a little bit of a interactive version of this? So there's still a couple of different ways to actually use these functions, maybe. Copy. Hmm. Everything takes a little while to load these days. Um, but we can start to get a bit of a feel for different types of policy gradients. And here, there's some code in order to be able to actually look at this. But basically, we can have different policy distributions. There's also different ways to actually be able to estimate um, basically this part. There's different ways to be able to do this model. There's also different ways in order to be able to estimate this reward. So you could have actually a pretty simple version. So I think this is a policy gradient. Could technically have something called a reward gradient. So this is not doing discounted returns. This is like reward after a single step. And the policy distribution looks like it's going to be some fixed variance Gaussian. So like the variance here is not going to change as the policy actually ends up learning. And the reward here is just a sinusoid function. So there's actually like multiple global optimums in this. It just has to be able to find one of them. And then can I move that a bit? Just kind of like start the training session. So all these little teeny arrows that you can barely see are basically the contributions from the reward that the policy ends up seeing in this training process. And it's basically, different things that are taken at different states in there is all telling it to go different directions. And then when averaging all these together across many, many samples, then it can actually get like a better landscape for understanding where the policy gradient should go. And you can also have some really, so let's chain this back to policy gradient. You can have some really odd looking reward functions. I think there was this one, train. So this one will learn to adjust. This is a really ugly reward function, but because of the way policy gradients work, where they're basically sampling, they don't really need to have too many assumptions on smoothness for the reward function or the actual policy distribution. It can still end up finding a pretty good output. This is also one of the reasons why people like to use these for like RLHF. It kind of works over any function class, even though it's still pretty like numerically expensive to be able to use RL. Like it might take a pretty large amount of data and samples. It's still pretty good at being able to find a good solution. Okay. Does that make sense? Feel free to like play around with this a little bit more. It'll help you give a better idea for the different types of the advantage functions we'll get into and different policy distributions. And I don't know, some ideas for how these things handle different types of rewards. Short story is actually these do not handle really odd reward functions, especially ones, uh, the noisy one. So this was a rough function. RL doesn't actually work too well with functions like these. This is an extremely noisy signal. It works the best when there's access to a clean, dense reward without a lot of kind of like local optima all over the place. It's one of the challenging things these days is still like deep RL methods. They do get stuck in local optima pretty often, and a lot of the work is put into them to get them to like basically avoid those local optima one way or another. Okay, so let's get back to some more of the details. Right, I actually code this up. All right, so one of the first parts to figure out is the actual computer projector system. No, come on. All right, slightly better. I'm really hoping nobody has epilepsy in this class, but I'll try to avoid that as much as possible. Okay, so starting, basically, we've got this problem. We want to be able to optimize this objective. So we're just going to go through like some of the background for why policy gradients work. Because to be honest, it's sort of like the nicer math background for being able to optimize these methods compared to what some of the other things we've introduced from before. So it's also possible to basically do this optimization in the infinite horizon case, although there's some challenges there. But normally, and what I'm going to talk about here is we're going to talk about the finite horizon. So basically, find the best policy that'll optimize the return given the next t time steps that the agent actually gets to interact in the world. Okay, so taking this objective, our first question is, okay, how can we use this? So this is it's an expectation, and that kind of starts to give us a hint about how to use this. With any expectation, we can take loads of samples from whatever that expectation is. And then from that, we can start to get an estimate of it. So that's basically how this is going to work. So for a policy gradient, in order to be able to understand, like right now, what is the current policy gradient and distribution for this policy, roll out a whole bunch of trajectories, gives us at least an approximation at the moment for the behavior of that function. So for any expectation, roll out n is the number of trajectories, t will be the number of time steps here, and then basically you've got at least that amount of data to estimate the current gradient. This is good because it's unbiased, because you're just like rolling out samples of the true process of how it works. Remember, with this, this doesn't work technically for when we're learning a model, because the model that we might learn that we could be sampling plans from can be biased. So it may not actually be something that's truly giving us an estimate of the actual returns the policy will achieve. But this is no model, take samples in the world. And it's nice and simple to perform. It's also been around, well, this day and age seeming like a long time, but I would still say 25 years ago isn't really that long, but depends on whether or not you consider the foundational model era, which kind of popped up 2 years ago as a whole new thing, and that's everything else is too old. Okay, but we basically want to be able to make steps on this gradient. Um, and this, in this case, means that, okay, if we adjust this policy gradient a bit, we're talking about adjusting the probability for these theta parameters, because those parameters are what actually are being fed. They're being used by our policy distribution. And then from that, that's what controls our actual like distribution of trajectories that come out of this model. And then basically you can use this to expand over the continuous variables. You can use sums or discrete stuff. This is a bit more, well, this is kind of a robotics class, and at least I have a preference for things that are continuous. So you're about to see a lot of integrals, okay, not a lot of summations. So in this case, if this is our function, we basically just need to compute the gradient for this over some integral. And this still, at the moment, if we're talking about this probability distribution over trajectories, depends on the initial state distribution and the dynamics. And we can't, at the moment, compute a gradient through those things. We don't have access to them, although we did talk previously about how to learn a model for them. But we also said that it was a terrible idea to try to compute a gradient through these models. So we can at least take a shortcut from this. So if we're evaluating from only samples, we can always do the nice trick of basically being able to do this adjustment, and then we start to get the gradient. This is just because, derivative of logarithm rule. And then this is something we already have in like a formula for. It's just our probability of trajectories all over again. So we can start to expand this, and then we just need to integrate over all of these trajectories in some way in order to be able to get us our gradient. So from here, shoot. Okay, still one more square bracket. Basically, now we can just evaluate this whole process with some of the samples. Now that we have this expectation But this is an expectation for the gradient. Before it was just an expectation for a probability distribution. Okay. So then unfortunately, because this has still got that dynamics inside of it, it's still an issue. So here we can unpack, remember this is our trajectory distribution, do the like almost most common thing that we always do in mathematics, which is just to multiply, like take the log of everything. Then this product ends up becoming just a bunch of additions. And the reason why we like this, which we're going to use in a second, is now we can take, what is this, expanded, basically stick this whole process inside of here. And the reason why this is nice is when we're going to end up taking this gradient doesn't depend on the initial state distribution anymore. And this gradient doesn't depend on the dynamics anymore. It just depends on the current policy. So we can get rid of those. We no longer have to worry about those terms. So then computing the policy gradient is now just like the log probability of the policy given the reward. Just like we can close our eyes now and not have to care about the fact that there's some rolling out of trajectories in this process. It's just this weighted process here in order to be able to get the gradient. Okay, I know that was a little quick, but any kind of questions about this process? This is kind of like sampling and policy gradient 101. And if you've got more questions, you should really go check out Sutton's paper on like the original stochastic policy gradient. To be honest, I love papers from those days. They just get right into like the math and sort of talk about it in a pretty pleasant way. And it's not like 80% of the time trying to defend itself from reviewers that just have a bunch of nitpicky comments. So it's a nice, easy read to describe like why this works. You just do it over some stochastic outputs and the math works out pretty smoothly. Okay. All right. So then now we just have to use this. That's at least part of the easy bit. So being able to compute this actual policy gradient. So now in this case, we're doing this expectation. So we can kind of pull this out. Now we just use this to collect a bunch of trajectories, at least n trajectories. Keep in mind that for a lot of policy gradient algorithms, n actually gets pretty large. So at least sometimes I've seen certain papers use up to like hundreds of trajectories that roll out. To be honest, n is a really nice lever for this type of algorithm. If your method isn't working very well, the most obvious thing to do is increase n, and then it gets a better estimate for the policy gradient, and it's more likely to make a step in the positive direction. It's one of the reasons why people have like grown to like using this algorithm quite a bit. And then from this, just compute, the policy gradient that we've discussed already. Use a little learning rate so things don't learn too fast and everything's pretty stable. And then just update the parameters. So this overall algorithm is really not too many steps. It's just collect a bunch of trajectories using the current policy. Basically just now sum over all the rewards from this in order to get the actual returns for each point on and state on the trajectory. Compute that gradient for basically which direction would cause, what would seemingly cause the reward for these to increase. Update the policy parameters. Do this until you're tired of waiting or your policy looks like it's basically started to converge. And this is the reinforce algorithm back from like 1992. And then interestingly enough, this is making a huge comeback because this seems to work fantastically for RLHF, even though there are now decades of newer algorithms for RL. Okay, does that make sense? Any questions so far? Everyone is a big fan of policy gradients? No? Kind of? You are? Mm-hmm. Simplicity. Can't argue with simplicity. Is like this is the algorithm is 3 lines. 3 lines and some extra compute. It's easiest to find extra compute or be a bit more patient. Because we're going to start talking about more things that are based on like DQN and Bellman updates, and then the math and everything gets much more confusing, and it's not as easy to get working. So this simplicity is really, really nice. It's why people basically use this algorithm exclusively for sim to real RL. They use it for training RLHF. possibly because the people who started doing that are not very good at RL, and this is the easiest algorithm to get working. So but it's also fairly sample inefficient, unfortunately, but we can work on getting around that. Okay, great. So starting with the questions, I can probably skip the scratch step here. All right, but as always, maybe the story isn't quite that short. And in this case, one of the challenges with these algorithms is they have really high variance. So if, for example, if you've got a stochastic policy and that policy is like one trajectory is rolled out from that policy, it's stochastic, so it means it's going to select a different action in every individual state. So if we, for example, if n was only one and one trajectory was rolled out, and then we run the policy again to compute another trajectory, very often, like the returns for those trajectories are going to be very different. And that's a problem because it's really hard to understand or basically estimate which direction the policy should be shifted if every time it collects data, the policy distribution looks extremely different from how it was from before. So this is one way to be able to overcome this, and this is what we're going to talk about here for a minute. So if this was basically the reward function, and here these are in some ways like visualizing the reward that's achieved or the current likelihood. And this is basically the process of being able to adjust some of these. So basically, this blue line is the current policy distribution, and this green and yellow is basically some of the rewards that are achieved. Okay, my apologies, I got that mixed up. So the blue line is like the current distribution for the stochastic policy right now, kind of visualized over like a one-dimensional space. And then the policy basically takes these three actions in the world, receives these three different rewards. So if the policy happens to basically get the rewards that are here on the left, how much do we think like that policy distribution is going to change? So there's really, let's say this is 0 here. So it's going to want to increase the likelihood for those small little green bars that are above 0. Right? Does that make sense? Okay, so that can be okay. But then if we start to think about, all right, how much do we expect that this policy distribution is going to change from that? So that maybe after it does an update, the policy distribution is ever so slightly different, slightly shifted towards those actions that resulted in slightly better reward than what was from before. Okay, that's not too bad. But then, so then what happens in this case now? Now just think about through the steps. The rewards for this are much higher than the one on the left. So there's going to be a much larger gradient that's going to be computed for the actual policy from this data. So in this case, all right, maybe show of hands, do people think this is going to move further to the right than the version on the left for the little change in policy distribution? Yeah. Okay, how about further to the left? It's my left hand. At least not sure about that one. Okay. Yeah, because part of the problem is basically the gradient points into this direction where those really large rewards are. In this case, it's maybe not only going to shift to the right, it's going to start to peak around this individual set of rewards here. And this is a really large shift. This is, if we're talking about deep learning, remember deep learning likes things nice and slow, and it takes small steps. Also because if there's variance over this, so this is basically rolling out two different trajectories, okay, these are really large shifts in the policy if it would match that much. It's going to be really hard for it to converge down to whatever are the good rewards, like the largest sum of rewards, especially if it keeps receiving these two samples back and forth. The policy might be bouncing back and forth between these two things. It's not going to end up converging too well. So then how can we end up being able to estimate this a little bit better? Like reduce essentially what would be seemingly large gradients for stuff on the right and almost insignificant gradients for stuff on the left, but we'd still want to learn from the stuff on the left even a little bit more. So one thing to be able to do is actually you can actually just add a constant. Is technically like mathematically correct here. And this will reduce the variance. So even if we just took this line, let's put it there instead. Technically, this reduces the size of the gradient, doesn't change the direction at all, but then at least the policy distribution should make like a more manageable step in the direction, especially if it's trying to combine basically the gradients from a bunch of different trajectories together. So then we're going to basically reuse this a couple of different ways. So one way is just to add a baseline. So from before, take the gradient, figure out a good baseline, and we'll get to the figuring out a good baseline here in a slide or two. But basically adding or subtracting something to a gradient doesn't actually change the gradient, doesn't make anything biased. It can help reduce the variance over the actual distribution. Okay, does that make sense so far? Any questions? Okay, it's basically getting into a bit more statistics. So the real question is, okay, what should this be? This, what we call a baseline for now. Nice. There's a lot of different options. One of the kind of like more like initial things that can be tried here is essentially we can just take all the trajectories, reweight them by their average. So if a bunch of trajectories are collected, then compute all the average like returns over all trajectories, and basically subtract that from the original gradient. And at least this is an average that's like somewhat centered over the data. So if there's a bunch of things that are distributed, it's just going to find the mean in there essentially, subtract it from that, and then there's going to be less, I guess, craziness going on in the data. It's also nice because then it actually helps ensure that there's some more positive values as well in order to be able to shift the distribution, which is often numerically a little bit better. And this can actually work pretty well. This, if it's just using the identity in this case, this is just a few steps to show that like adding a baseline doesn't end up changing the gradient. So this isn't introducing any bias in any way. Makes this convenient identity. And then from this, you can kind of show that this normally ends up helping improve learning, because now at least it's always this problem of we've got some data, even if we go collecting it and there's an automated way to go collect it, how can the agent or the algorithm extract as much information from that data as possible? And we don't want the policy to kind of like overshoot its behavior either. Okay, makes sense? All right, and this is not a small area of research. There's a lot of different papers on what is probably supposed to be an optimal baseline here. There's also the generalized advantage estimation, which I think was one of the papers that was assigned, which is just another way to try and be able to estimate this, while still doing a bit of a balance between some of these objectives, because it's possible to both like use that baseline as a sum, but that sum actually is now going to shift every time we collect data. So now there's even an amount of variance in the way we compute that baseline. So sometimes people will learn for different algorithms what are called critics or value functions, and that'll be a current estimate for how the policy performs at that state. But now when a model is learned, it often introduces a bit of bias. So something like GAE here is kind of a balance between using a model, because then at least it does a better job of kind of like amortizing the computation of the current policy's performance, versus using stuff that's directly from the policy's data, which has more variance. And it's basically, there's a long game and many papers that are trying to balance these two pretty well in order to be able to improve policy learning. And if you look at some more of the recent papers and some of them that we'll discuss at the end, there's basically, using some version of this GAE where it's going to learn some model for the policy's current performance and then kind of weight it a little bit by the actual data the policy just sampled. But that average behavior often helps a lot. Okay. All right. So those were kind of the positives. The challenges with these methods is that they're very inefficient. So there's basically no reusable model, and the entire process is trying to learn over an extremely, well, somewhat noisy gradient estimation process. So these are basically just things that come along with this algorithm. It's really hard to be able to overcome any of these completely. This is why there's a lot of papers on this one, because it's kind of easy to pull out our book on statistics and figure out how to basically get a better estimate for the policy. These other ones are a bit more tricky since there's really no reusable model. However, like I said, it's still really hard to do better than that pure simplicity of this algorithm. So it still like almost always works, even if it's sample efficient. So then basically, does everyone kind of get the point I'm getting at? So then like what types of problems are good to use this type of algorithm on? Anybody have any thoughts? No? Any questions? Uh, what types of problems do you think we're not going to worry about sampling? Hint. Yeah. Yeah. If you got lower dimensionality, um, I remember sample efficiency is kind of determined by the branching factor, which can kind of be related to the action dimension, and then also like the length of the trajectory. So if you've got something that at least doesn't have a really high action dimension or number of states, then it can work pretty well there. Yeah. Any other ideas? Mhm. Are there certain types of environments where it's really not expensive to be able to sample data? Yeah. Well, so yeah, for the most part, everyone seems to think that a simulator is basically cost free in terms of sampling data. So whenever we have these types of problems where we're actually in a pretty lucky scenario that we've got a simulator or basically sampling from the environment is almost no cost, then this is a really great tool to use there. And then as we'll get into this, there's a lot of examples for this. This is where people have used it to play the game of Go or kind of like any robotics simulator, because these are pretty easy to sample from. I mean, Go, how many people have at least played Go before? Couple? Yeah. The dynamics for the game of Go are pretty simple. It's a grid. You place, I don't actually even know what it's called. You place a stone. There's nothing extremely complicated that needs to be simulated here. So this is a pretty cheap simulator. And this is a great sign for this algorithm. It's like, great, we can totally throw a bunch of compute at this and basically have this enumerate all of the possible plans, even if Go seemingly has like a really kind of complicated branching factor. It doesn't matter in this case because it's just so easy to simulate. And at least if you've got enough compute, like some of the people at Google, then you can roll out like every possible trajectory from every possible configuration of the game. To them, at least for that particular project, seemingly simulation was free. And that's wonderful. Then we can just apply algorithms like this really well. So things that are games that have kind of like really well designed simulators, or the physics or dynamics are really well known, is a good place to be able to apply these algorithms. They don't often work out as well in the real world, just because it's very expensive most of the time in order to be able to collect data in the real world. And it's not, you can't just enumerate every single possible case, because you'd probably enumerate a whole bunch of stuff that does not matter, and it'd be a large waste of time. Okay, great. So part about this, okay, let's dig a little bit more into like, why is this so inefficient? So policy gradients are inefficient. One of the key reasons, basically the policy gradient and the way the math works is that it needs to take like data, and it can only use that data for one single policy update. So it might need to collect, like 10,000 samples before it can even make one gradient step on the actual policy. So this is a really bad ratio. Like we wanted to at least be able to take more gradient updates, be able to learn more from that data from a much like fewer number of samples in the real world. And this is really related to this part. Like this expectation is actually over the trajectories for the current policy. So the only time this gradient is unbiased and works properly is when it takes a step on the current policy at the moment. Once one single gradient step is made, technically, the mathematics doesn't apply anymore, and that expectation is going to be wrong. So any additional steps are going to, at the very least, be unbiased. Any more steps than that are going to be, I'll say, risky at best, since the current gradient is not like the current distribution for these parameters are no longer going to be represented by this expectation. And everything starts to get pretty murky at that point. Okay. And this is basically through this process, it's this here. So there's always a collect and the number of trajectories. Take one single step. And you see like there's no replay buffer here. There's no data set. That's at least because for the algorithm, not allowed to keep around any data after any gradient is made because it's not technically correct anymore. So it's, again, a nice mathematical framework. It basically doesn't have any of the ingredients that we want for robotics. It's horribly sample inefficient. It doesn't reuse any data. It doesn't have a model. It's nothing we can expect. There's nothing we can reuse. Not a really great place to start, but we'll talk about how to overcome at least some of these challenges in this algorithm. Okay, so one, in order to at least be able to use this gradient a little bit more, or at least the data that's been collected so far, is to get over this problem, and is basically to replace this with a sampling distribution. So here, it means that we can do a type of what's called importance sampling, so that it's still at least possible to be able to use some of the prior data. But so we need to be careful about being able to use a bit of that prior data for a few more gradient updates. You can look into some more of the details for importance sampling, but basically what the process does is, okay, the policy can still take a gradient. It can still use some of the old data from the previous version of the policy, but it's only allowed to use that old data with respect to how much that data would still be likely under the old policy. So basically, as policy updates are performed and they get further and further away from that original policy distribution that collected that data, basically the gradient is now going to reduce the weight for that actual gradient because it's less likely this actually came from that original data. So in this process, it's basically what we get here is if this is the original data distribution, like how likely that data was under that previous policy when it was collected, and this is how likely that data currently is under the policy after it's being updated. This will slowly kind of downweight gradients as they get further, as this distribution gets further and further away from the distribution of data that it was collected from. So it's kind of like, as it's less and less likely to be generated from this policy, less of the gradient can be contributed to the actual update process. This is a very kind of hand-wavy description of what the math is describing right now. But this is also what's used in pretty much all of the policy gradient algorithms these days, is some sort of importance sampling ratio. And this allows the policy to at least take 10 to 20 updates on a set of data before throwing it out. Once you start to get beyond those number of updates, then basically this ratio starts to get pretty close to zero, and then really nothing is contributing. It's actually kind of a good way to be able to tune how many gradient steps you can take for your importance sampling is just check this ratio, and you could maybe even skip taking some gradients if you're worried about, saving that much of your compute budget, something like that. Okay, does that make sense? This importance, I'm introducing this importance sampling ratio because you'll see it in pretty much every library you go if you're looking at something for PPO. But importance sampling is a pretty old concept that's used for basically combining lots of different types of probability distributions. So if you want, you can go dig into some of the details for those methods. So this becomes nice because the whole point of this really is to try and be able to essentially use off-policy data. As soon as one gradient step is performed on the original policy, all the data is considered off policy. And now basically this process will, if this is our old policy gradient, introducing basically this important sampling ratio that will adjust things according to how much the likelihood of that data under the new policy after it's been updated. And now we can at least use this version of the policy gradient repeatedly to do a few more gradient updates. It's not much, like 20 steps on 50,000 samples is actually quite terrible, but it's at least better than one. But we'll slowly get closer and closer to maybe getting a 1-to-1 ratio at some point, but it's almost impossible to do with these algorithms. And if you want even some more details, you can look into like the retrace and vtrace paper. These kind of show, okay, that if you at least pick some of these important sampling ratios a bit more carefully, they will still always have your policy converge and they won't mess up training or like the algorithm essentially. And these are used for a couple of different things. So even like the Alpha Star paper uses vtrace. It's training a bunch of policies to play a bunch of different games. So a lot of the data is off policy because then it shifts. It basically sends gradients back to some other server that's collecting them and applying them together and then sending those back up to policies. So everything is a little bit off policy in this distributed training process. This is where one place where I've definitely seen this be pretty helpful. If there's a lot of stuff like the A2C and some distributed training where a little bit important sampling saves them a lot, even if it only helps them like be able to be like a second out of timing with some of the other policies, and everything still works. So sometimes even these little changes are quite helpful. Okay, any questions? So far, all totally makes sense at the moment. Okay, you won't see stuff like vtrace or retrace in too many papers, but you will see this in most code bases that I've seen so far for PPO. So at least you know why that's there. Okay. So we talked about a couple of the issues. Let's talk about, okay, let's say some of the tricks, because there's actually a lot of them. But we'll start from this process here. Okay. All right, actually, why don't we take a break since we're already a bit over. It's 2:05, so we'll start again at 2:15. And then we'll get into some more of the real tricks, because there's actually like 20 to 50 of them, but we'll only go through a few of them that are most important. So, relax. Hey, how's it going? Okay. Mhm. Build images with blocks.
Yeah. We build actually like blocks and try to like create structured address image
Okay.
and we were just this year we mentioned that so for example like a house.
Yeah, but at least in this section, it doesn't say anything about blocks or a house. It says use a VLM to predict the next action.
Okay, so
We could say about pretty much any model. Probably mostly because didn't yet see what was on the next page.
That's like that actually. Yeah, we were just wondering if there's something. Yeah, just.
No, I think like you've got the picture on the next page a little bit more for some of the blocks, although this is kind of drawn. So I don't know what physical blocks you're going to use.
Yeah, 3D print the block.
Okay. You've got a 3D printer?
Yeah.
Okay. Okay, let me know because there's also one in my lab and one here at Mila. They need to print off more blocks. Okay. Hmm. Okay. But then in the future, so we're going to kind of like every couple of weeks we'll do like updates to this, but include some more examples. So like what is going to be the picture here, like that you're actually going to use. Because at the moment, this is a bit hard for me to understand, like how many blocks will be. I'm not taking off points for any of that kind of stuff, but I'll give you better feedback in the future. Like show me what you're literally going to tell the robot to do as if I was the robot. And I'm going to.
It's going to be like an drawing or something like that. And the robot can try to match my picture.
Okay. I would, at least in the beginning, recommend, I wouldn't call it cheating. Like, don't do a hand drawing. Like, put the blocks together how you want them to look. Take a picture of that so that you know, like, that's scalable. And then maybe get into, like, more of the freehand to see how close it approximates what you do. Yeah. Yeah. Okay. Sure.
Yeah, like two projects. The first one is like to use the VLM to do like the planning. And then after that, we intend to use Colab. It's like you condition the motion planning from the equation. So, for example, avoid this or like everyone's like okay, go
Mhm.
so that's something that we can also. So it's like it's
Okay.
so because the first part, there's no training involved. But if it's like there's training involved, if you have like a point of
Mm.
we are able to take a part or like the training is mandatory for the project.
I mean, the training isn't mandatory as long as you can show me that you're using stuff from the class that'll be helpful.
Okay.
But actually, what I would say in this case is, okay, you should absolutely do some training, but you should do the simplest stuff possible. So, like, what are you going to compare this to? Like, you should at least take like PPO and run it on this task with like no information and see how well it does at stacking blocks. Because then at least you can say like you ran something, you learned something, and then at least you know if your method, all of this VLM work is actually doing better than just like throwing the simplest algorithm at it.
Yeah. I feel like it would be like harder to because
Well, just take and use PPO. You don't have to re-implement it. Like take the one from CleanRL and just run that for your task. Yeah, give it the same input, and you'll still have a reward for like when it's successfully rearranged the blocks to be able to do that thing. It'll also really help because okay, the one of the areas I can see this like accidentally not working well is trying to make the reward function for this. So that's why it's like it's often a way to the only way to debug that reward function then is to basically set up like clean RL with some RL algorithm and then run it and make sure it still does the task you expect. Otherwise, it's not clear whether or not the reward function that you're going to make from this for the VLM is actually like capturing what you want it to capture. So there's many reasons to just like take PPO and run it with your reward, just to make sure that you've got some baseline comparison, but also that your reward function, because you're going to probably create one with the VLM, aren't you? Like here's a description, here's an image.
there's no training. The goal is just training the PLLM. The goal is just like create some instruction. And then to use as baseline for the server part, the feature base from
Okay.
so with that, like you mentioned that some people have access to Gym API, so
Yeah.
so since it's not like connected to it
Is it connected to move it? I added Kirsty to the Discord channel, but you should ask this question in the projects like group. Just like what is the API for this? Because actually there's a simulator for it already, which I think uses blocks. So you could just add a bunch more blocks to that simulator and start having it learn to stack things with a few more, with probably like a bit more software engineering for the simulator. Yeah. But yeah, send me a message for that one so we can start it on that. Yeah, on Discord. Yeah, that reminds me. I actually mean to. I'm gonna make a channel for every one of the projects so that we can each of the teams can chat about their projects in the Discord channel, and then Kirsty and I can chime in and see whenever you need help. Okay. Sure. Yeah. Hmm. 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 All right, let's get started again. Also, partly because I wanted to at least make one quick comment about the projects. So, um, like I went over most of the proposals. They all look pretty good. Some, but just make sure to follow the template a bit more next time, because then I at least know you kind of like hit everything on the project, and then I worry less about forgetting certain things to make sure that it works well. But two other things just to consider. One is to try to, we weren't kind of at this point, but try to put some sort of baseline in your project. If at the very least it helps debugging so many things for your project, or like you should take PPO and run it on your task. And if it may not work, but the idea is to do a little bit better. But like half of the projects, people are kind of like designing stuff that might need a new reward function. If you're making anything that has a new reward function of any kind, you should run some RL algorithm and make sure it still works before just putting your algorithm. You kind of want to reduce the number of places things could potentially go wrong. And having a baseline will always help because then you'll just know, oh, well, cool, my stuff does do better. Or you can look at what the baseline does and be like, I can do better than that or something. So it often gives you a lot of good background information about what's going on. I think that's about it, except for one more thing. Okay, so for the projects, I'm going to make a bunch of channels on the Discord channel where I'm going to put everybody in their project group, and then you can discuss your project inside of that channel. Also helps because then like Kirsty or myself or Michael, who's the TA, can easily answer questions when you've got questions about stuff in there too. So you can kind of keep your chat there. And I just announced some stuff, but yeah, and then we'll kind of go through this process every 3 weeks or so. Basically, there's going to be another step for the project. And basically, the next part will just be like, we'll put in a little bit more detail for your method, et cetera. To the point when we get to the end of the class, you really have like very little to write for your project because we'll already have gone over most of the design. And you'll just have to put together a proposal or, sorry, a presentation at the end. Uh, yeah, I think that's mostly it. Although at this point, like the projects are out, so a good thing to do is probably to like at least spend a day a week working on your project starting from now. 2 would might be a little bit better. And then there's a little bit of a curve too, like for, well, if there's a group with a lot of people in it, there's going to be a higher bar for what's expected for that project. And if there's a group with one person, I'm going to balance these a little bit from, this always happens every year, but just keep that in mind. If there's 3 people working on a project, I would hope to see at least twice as many milestones passed for other projects since you've got 3 times as many people. Okay. Any other questions about the projects, concerns? All right, great. All right, so let's get back to talking about these, like probably baselines you should at least consider using so that you know your method is working well. But so tricks in order to be able to get these to work a little bit better. So policy gradients have really high variance. Supervised learning basically doesn't really have this problem, not the same kind of variance, because it's not variance in the gradient every time data is collected and what it's estimating. So basically, there's a lot of methods to be able to compensate for this variance that's introduced in estimating the policy gradient. Like I was saying, one way to be able to overcome this variance, make your batch, what is called batch size here, much, much larger. It's essentially the same thing, but so far of what we talked about, it's actually increasing n, like increase the amount of data and the number of trajectories that is collected, because this should basically reduce the variance over the estimate for the policy gradient. Finding a good learning rate, extremely non-trivial. Any idea why finding a good learning rate is really non-trivial for RL? I've got a question for you. When do you know your RL policy has converged and been optimal? Ever? Maybe? So no, basically. It's unfortunately a version of the halting problem. So it's kind of like we don't really know for a deep RL policy when it actually converges. It's kind of like an unwritten, really terrifying rule inside of the deep RL community that everyone just sort of picks, all right, we'll do 5 million samples, who knows, or 50 million or something like that. And then wherever these numbers came from were just kind of pulled out of a hat after lots of practice. But at 5,000,001 can be when the agent finally finds like the trajectory that is the optimal trajectory. We never entirely know when the agent has reached absolute like optimal policy performance because we don't technically know what an optimal policy is when we start our RL. So it's sort of like, well, this means we can't really anneal the learning rate because at 5,000,001 is when we finally find the trajectory that's optimal. And we want to learn that as best we can now. And we don't want our learning rate to be teeny and unfortunately, what happens a lot in the community is basically those trajectories are ignored because the learning rate becomes so small, everything's already been annealed. It basically is a small contribution to the one step in a policy gradient, and then it's forgotten. And this is a challenge for the community. So this is why it's really hard to find the right learning rate. Usually people stick with something kind of small and then don't really change that. In fact, in many papers, the learning rate is never really annealed for RL. It's usually something like 10 to the power of -3 times 3 to the same thing, 10 to the power of -4. Something like that is usually an okay place to start, at least for policy gradients. Nothing too great. So I explained a little bit about like why the annealing doesn't really work. You can go ahead and try Atom. That can help a little bit, but it can still cause a bunch of other sort of weird issues. Yes. Ah, kind of. I'm going to introduce some more tricks so it becomes less zero. But basically, if you just think about like estimating it and you have a baseline, then at some point, basically the policy is performing as well on average, and there's no more rewards that it's receiving or returns that are higher than its average. So there's really basically no gradient. although some libraries adjust for this in a kind of clever way. But yeah, when it starts to reach convergence, then yeah, gradients get real small. You sort of want to increase. Okay, from a supervised learning perspective, it sounds like, okay, this is a good time to increase, or sorry, I guess decrease the learning rate. It still, in practice, doesn't end up working very well because we don't know when it's converging. And instead, what people tend to do instead is actually reduce the exploration noise. Because usually it's sort of like the policy has reached a place, the gradients aren't big enough or some in order to get it out of the local optima. But actually, if we decrease the exploration noise, we also kind of decrease the probability distribution a little bit, which just makes it a little bit sharper in that case. And then it can start to pick up on some gradient information there. So remember, there are many different ways to change the size of that gradient. And the learning rate one isn't often the best way. Yeah. Okay, good. Even if like Adam will sort of try to do this too, because it's going to keep statistics, and when it's getting at the end of learning, it's actually going to start adjusting the statistics for the learning rate a little bit. Sometimes that helps. Most algorithms seem to use Adam as the optimizer for RL. Take. I'm just going to skip that. Okay. So the variance for the policy is still a bit of a challenge, even if we can make it lower. The baseline might help. So if we're lucky enough to get to a plateau where we can actually reduce the learning rate, that's great. It's not too often that it's easy to get there. Because part of the problem is the baseline reduces variance, but there's still quite a bit of noise. Like the gradient can be quite large and cause a lot of those large shifts. So if you remember this diagram from our first class, the problem with this is, okay, the agent comes along, it samples a couple of trajectories, they mostly go this way. And then so it makes a large gradient update this way. And now the policy distribution is over here, just at the edge of this thing. At least a bit scary so far. If it falls off the edge, just literally think about as it like destroying the statistics for your like deep policy, such that it'll be unrecoverable, because that's pretty truly what happens. And then to overcome this, the policy gets stuck over here on the side. It's like, oh shoot. So it takes a couple of trajectories. They all say to really get back over here before the policy ends up falling off the edge. They all end up providing a really large gradient. The policy overshoots and falls off the right side of this cliff instead. And this is like a visualization of what this is. Called a policy gradient, but it's a stochastic policy gradient. There's basically a whole bunch of noise, and this thing can jump around back and forth somewhat uncontrollably in order to be able to make these updates. Okay, so we need something to at least allow this to not fall off the edge. Like when we all go for a hike up a mountain like this, usually some nice people have installed like a guardrail on the side, so it's at least very difficult to fall off the edge here. So then we need something that's basically the same purpose here. And this is if we look at this just a little bit more, like kind of a general problem for stochastic gradient descent, but a little bit more of a problem when we talk about doing stochastic policy gradients. Because the gradient magnitudes can change wildly because there's lots of variance in them. And then often when they change a bit, they kind of build up onto each other and then increase in size even more. And this is because changes in parameters can have really large effects on this distribution. Hopefully everyone can see that part down here. So that like actual distribution that is the trajectory distribution from the policy. Okay. Fortunately, so like one of the first things we could think about trying here is, okay, well, can we at least prevent the parameters of the policy from changing too much? That way, there's going to be some limit on how far this policy will shift, such that hopefully it won't actually get to those like edges of the cliff and actually fall off. So we can basically just take the gradient update that we had from before. All right, and then we're also going to add basically this this constraint. These parameters should now not change any more than this epsilon amount, very similar to a lot of the regularizers that are used in supervised learning. Okay, so then what's the problem with this version of being able to add a constraint or some regularizer? Any thoughts? Yes. Hmm. Yeah, do you mean the hyperparameter for like even the epsilon here as well? Or for the network? Sorry? Hmm. Um, that's part of the tricky challenge here, but there's even more to it than that. Because here, if we constrain something by the parameters, how much is that actually controlling the way that the policy changes? Trying to think of an example here. So what if, okay, there's two ways to think of this, maybe a bit conceptually. So if there was, okay, I'll pick a person that's actually trying to go up that cliff. And one way, there's kind of like two ways to tell them how to do things. I can either not really tell them, don't jump off the cliff. All I'm going to do is I'm going to attach a 10-pound weight to them. So like now you can't build up more momentum or something like that. But the other thing, the thing is this may not really prevent bad stuff from happening. You could also have a pretty malicious other agent come along, pick up that 10-pound weight and like hurl it towards the actual edge of the cliff, which the deep learning process can do that. But what we really want to say is like the distribution of actions that are produced out of the policy should not like be anywhere near this distribution. And like controlling stuff in the parameter space doesn't actually, well, in the more succinct way, let us know what the probability distribution is going to look like coming out of the policy. This just says don't get too far away from that weight, but that weight doesn't really control more explicitly the behavior for the policy. So you're really close on that part, but what we really want is not to constrain just a weight on the parameters, but how much the distribution between the old policy, which is this part, and the new policy, the actual outputs, the inputs and outputs shouldn't change. So we should be looking at this in terms of probability distributions, not just on like a sum of values between weights. And then now we can say, all right, make sure that the probability distribution isn't shifted too much, because then at least, the behavior between one gradient step to the next one has some sort of limits on it that methods like these don't really imply. Does that make sense? This is usually why for like a lot of papers, they kind of say like, well, use the KL distribution as a constraint. The regularizer here uh, doesn't really imply the same sort of structure. And now this, it's like now if we go back, sorry, come on, to this diagram, now it's like there's an actual constraint. Now the outputs from the network can basically not go beyond this little bubble. And each time that happens, so the agent can make a step kind of in this direction. And then there's a new little KL constraint that says it shouldn't change any more than this much distance away from where it was from before. And this provides a little bit more structure. Ah, shoot. And this is where, we want this parameter up to be like independent of any kind of distance measure, but the KL divergence works very well in this case in order to be able to control how much these are changed. For those of you that maybe read the TRPO paper for today, which is basically all about this problem and on how to do it a little bit more carefully in a second order sense. This means having to compute sort of the distance and then be able to estimate this. It's actually kind of complicated to be able to do this in terms of what you actually need to estimate. You basically need to compute the Jacobian of how like the policy distribution is going to change. So this isn't like a cheap operation in terms of memory or space, but basically either these all mean the same thing. So this is either the Fisher information matrix, if you're more of an information theory person, or the gradient vector product, if you're more of a mathematics person, or a Jacobian if you're more of a robotics person. They're all really the same thing here because this needs to be computed to understand like if a gradient step is made, how much is that going to change the outputs of the network such that can actually constrain these properly. And this gives us like this gradient of these two different functions together. So this is at least conceptually a nice thing to do. Seems like it'll control things well. Does not scale well. Even though like the TRPO paper goes over a lot of this in detail. So basically you can solve for this gradient vector product, introduce this constraint, and then figure out, okay, like how many steps can be made to not end up violating that constraint. So basically for every gradient update, there's kind of a bit of a line search that makes a few gradient steps until it gets to the end of that barrier and then doesn't let the policy change any more than this epsilon amount in terms of its distribution. So you're welcome to go look at the TRPO paper in order to be able to get some more details for this. But long story short, no one really likes second order optimization. So very quickly, there was a lot of studies like how can we basically get all of these benefits while not having to compute so much complexity? So is there an easier way? Yes, maybe there's a first order way to be able to do this. So basically, because this process for computing this is a bit slow, is there ways to be able to do this a little bit more kind of like first order? So here, this is where PPO started to introduce this clipping term. Actually, if you go back and read some of the earlier PPO papers, they tried about 4 different things and the clipping thing worked about the same. They also tried using some like Lagrange multipliers, which would basically have this KL term and then increase the weight of this KL term as training happened and then decrease the weight of that KL term as it was starting to get like not so far away from changing. But that was more unwieldy and tricky to figure out how much to increase that Lagrangian multiplier. So here instead, basically this clipping term is used where basically you kind of like change the policy up to some certain amount that's actually allowed beyond, what's currently in the data. And then beyond that, just kind of treat the gradient as flat so it doesn't cause as many changes. So now this is, recall, our important sampling ratio that we talked about from before. And then basically using this clip term, take the minimum of trying to make a step along the actual advantage, and then clip basically the amount of change that will be allowed here with respect to some small epsilon. And this will basically just kind of like flatten the gradient outside of anything bigger than this epsilon value. So this is sort of a, it's an approximate way in order to be able to do that nice KL constraint that was discussed on the last slide. It's also, but it doesn't cost nearly as much to compute. So if you wanted to, for example, train OpenAI 5, which was an enormous network and a whole lot of data, then at least this can be computed without consuming an enormous amount of memory. So it can at least fit much more network onto the GPUs in that case in order to be able to train. And then this can like train much faster. You can spend more time collecting data in the simulator and less time propagating and computing gradients and gradient vector products on the GPU. Okay, great. Any questions so far? Are people familiar with PPO? Like used it before a little bit? Okay, this is kind of like PPO, this particular algorithm is more or less everyone's like go-to for RL because it's not too difficult to code because some RL algorithms are kind of difficult to code. It doesn't have too many hyperparameters. It tends to work most of the time compared to other algorithms, depending on what you want to do. So if you want to try some RL algorithm, this is always a good place to start, at least if you're not worried about sample efficiency. If you're worried about sample efficiency, then you're going to have to stick around for the next 4 lectures where we get into RL algorithms that are much more sample efficient. But they are also a bit more challenging to code and have a little bit more baggage. It's maybe one way to put it. Okay, so I've got a couple of examples here. I don't have a whole lot of time left. Let's see if this still works. So the nice part is, like I said, sort of like if you've got compute and time, you can always just stop collecting more data. Jeez. Hopefully everyone is enjoying their commercials that they get when they live around here. Good gosh, come on, go away. Finally. So you can train a lot of agents to be able to do stuff pretty simply. So at least from a couple of years ago, you know, one of the large challenges was basically trying to create an RL algorithm that would work, in this case, like from scratch about across a bunch of different tasks. Like that used to be part of the challenge. It's these days it's being able to do zero shot training. But this means here, this was just like starting from scratch, this RL algorithm would work to be able to find a pretty good policy for any of these morphologies across a bunch of different terrains. And there were could use the same hyperparameters for all of them. I think it only took a day or two to be able to train because the simulator was pretty fast. And then it's just sort of, it started to work pretty well, as long as at least you had the time. A couple of different examples and different algorithms. All right. Now you're welcome to go look at some of these papers afterwards. These are at least a couple of nice, good examples that just show like PPO just kind of works. You reduce the variance a little bit, you collect enough data, make small incremental improvements in how well the policy works. So you kind of can't argue it. It's really hard to argue with these algorithms because they do make a somewhat good monotonic improvement while training after the parameters are set up pretty well. Uh, although, so from RL perspective, this works. If you ask any robotics person or any computer animation person about how well the behavior looks, they're gonna probably have some complaints. So you probably would not directly apply this to your like humanoid robot. And to be honest, the best thing to usually do there is you need some data from people moving is the best way to regularize these types of motions so that you at least have some constraint. It's not a constraint, but some additional reward for like matching a normal walking behavior. And I'm pretending I have a normal walking behavior. It's usually kind of weird to walk in front of a crowd, whatever. Okay. So those all work really well. You can go look at some of the train adaptive stuff too that I did as well. Basically use the same concept with a couple of other bells and whistles to deal with some other multimodality problems. One of the really nice parts is, okay, remember that reinforce algorithm that was like 4 lines of code? Yeah, sometimes that's as much as what's needed for the actual Python training as well for this policy. It's just basically make a policy like very similar to what you did for homework 1, although now it'll be a stochastic policy. Compute the negative log likelihoods for what has gone off the screen, but this is for the actions that are actually collected. Compute the weighted part. So this is basically that function, negative log likelihood times the like returns for or advantage for each objective. And then just like propagate the gradient. That's basically the entire algorithm. There's a few more methods that kind of sandwich around this to make sure the learning rate isn't too bad. But that's it. This is another reason why it's nice and easy to use. Okay. So a little bit about assumptions, which I wanted to get into a bit more this year. Um, because, so like, what are the conditions that allow these algorithms to work? So one of them in these details is, well, technically the policy needs to be a bit smooth such that there's going to be shifting in the policy distribution for updates. Okay, but the one I kind of want to talk about more, at least for a bit here, is what's called ergodicity. So I will explain ergodicity and then you can all tell me why this is not great. But ergodicity basically means, okay, the policy needs to be able to reach every state in the state space. There shouldn't be any state it gets stuck in forever and can't get out of. And it still needs to have some probability for like revisiting the same state because then it needs to be able to do that to be like actually estimating the policy gradient. So, all right, can anyone give me an example of a state that like a robot can get into that it can't get out of? Any thoughts? This isn't a trick question. There's actually tons of them. It happens all the time. Yep, it's stuck probably forever, unless it has some friends that'll come help it out somehow. Yeah, so that's at least one example.
jump far away. What was the job?
Yeah. So there's all sorts of these examples, which then if we're looking at this and for these algorithms to work, they need what's called this ergodicity. It sounds like it's never going to work for robotics. There are so many places where technically a robot can get stuck. I also gave that example at the beginning of the class where like if a robot's trying to manipulate an object and it drops it on the floor and it can't reach the floor, all right, this also is not going to work. So this is why in that a very original piece of work I was talking about from today, the robot was designed to pick up items off the ground. It's because we carefully kind of considered, okay, what type of tasks aren't going to cause problems with the ergodicity for this algorithm? This is often also really frequently called the reset free problem for agents, which basically means we basically can never call environment.reset. There's never going to be some other mythical system that like comes in, reconfigures the world after it's like dropped stuff or fell into a hole that'll get it back into its perfect state again. Because that's not really something that is available in the real world. So there have been lots of algorithms that essentially try to do what's called reset free RL, where they either like carefully monitor when they start to understand when it's getting close to some of these states that are called sync states that essentially can't get out of. And if it gets close to those, avoid them, like they're basically poison, or some other ways to kind of avoid or have the fewest number of resets in this process. But just keep this in mind that like at least one of the less realistic assumptions for these algorithms is that they need this ergodicity. And that in most simulators, there's always just like a reset, go back to the beginning of the game again, try again. But that doesn't really exist in the real world. And I don't know about you, but I don't want to physically be the person performing these resets all the time. That can actually be a lot of work. And at least for some of the fun things I've seen people do, is they will use a second robot that basically performs the reset for the learning robot. The second one will require a fair bit of engineering and design from the actual humans. For example, for a lot of those manipulation problems, I've seen people like design what is basically a funnel underneath the robot such that it collects that item and another one comes in and grabs the item and puts it back on the table, just in order to apply this like sort of type of reset that allows the robot to continue training to kind of essentially make everything ergodic again. Just watch out for those. You're probably better off, at least that's what I did, is find a couple of problems that don't have ergodicity problems, so you can at least collect a lot of data there and automate those. There'll be people basically avoiding problems that have lots of ergodicity issues, or that's where people at the moment are collecting data by hand, like using VR systems and things like that, because in the exploration, there's a whole lot of essentially sync states that would cause issues with autonomously collecting data. Okay, does that make sense? Any questions? It's kind of like pretend they were children and no parents around to get them out of the messes that they get in all the time. One other way to think about that is like maybe we would totally solve making AGI robotics if we just gave them to parents to figure out how to grow up and we don't have to worry about any of these algorithmic problems. That's the kind of, I don't know, backward view of that particular problem. Okay, great. So, okay, so yeah, I'll cover this for a bit. One variant on these algorithms are what are called actor-critic methods. So this is all the same stuff here. But there's still a lot of like variability in being able to estimate this. So maybe there's a way to essentially figure out how to estimate this variability a bit better using something called a critic. For example, sort of like we were asking about, like what happens when the cumulative reward is 0 and there's no gradient, even though it's sort of just like the average behavior for the agent. So we basically talked about this option for being able to introduce a baseline, and that helps adjust the variance for this. But this is also still pretty noisy because that baseline will change after every like batch data collection problem. So this can lead to, so at least in the terminology, you might sometimes see G, like in Sutton's book, Introduction to Reinforcement Learning. This is often what's called the reward to go. We're trying to estimate from wherever the agent is at that state, what is the like mean or estimate or reward and expectation or return and expectation from that particular state. This now, we could use this as a critic or basically learn a model that'll estimate this for the particular policy at that particular state. So one of these is called the value function, which is basically what's going to be the value from this state given this particular policy, or the Q function, which is essentially, what is the value at this state if I take this action? And this is what can now be used as a critic, where basically if these things are now estimates of the average behavior for the agent, if the agent finds an action that results in better than average behavior, great. The critic says, do that action more. Don't do do less of what you were doing from before. It's essentially applying or like being able to be used to show that gradient that was available from before, but now it comes from this estimate of the agent's behavior instead of like right from the current data. Fortunately, we can train a model for this. It's not too difficult. Like even if we're just training a value function, you could just train this value function to like, you've got data for the next T steps, just supervised learning, train that value function to predict what'll happen for the next T steps. At least to help kind of pull this together though, because there's many, many different types of critics. There's different ways of thinking about them. So reinforce that didn't learn a model at all is basically just straight up using this reward to go. There's the TD Actor-critic, which is basically like one step, just says, okay, if the current value function, well, if the value at the next state plus the reward that the agent got is slightly better than its average, great, then that's at least a one-step estimate of getting a better advantage. There's a complete like advantage function that at least can take into consideration, more rewards into the future. And there's sort of straight up using just the Q function as a measure of saying, okay, well, this thing literally gives us a function. And one of the inputs is action. So we can kind of like connect those two together and just say like, which direction should I go to increase the Q value? And push that gradient back into the policy as well. Okay. Yeah, I'll just cover this last little bit here. So one way to be able to train these, you can just use supervised learning on the value function. You can also use Bellman updates, but let's stick to this for now. Sorry. For these two different options. And then, yeah, just computing the sum of future rewards is just computing that reward to go. So you can just use supervised learning to basically be able to learn this. At least for a value function is a little bit simpler than having to train a Q function. Although in practice, it seems training this using TD error instead of just supervised learning works slightly better for a few different problems. And then from this, technically we can estimate the Q function if we have access to the reward at for the next state. And this is where you can get things like the advantage function, which is just the Q function minus the value. It says like how much better on average is this action at this state. And one other way to estimate is these two. If you want to know a little bit more about the details for like these types of critics, I recommend you go read the generalized advantage estimation paper that kind of goes over many of the details between these types of critics and finding a good way to kind of like balance these together and still get pretty low bias and variance when using them as a critic. Okay, let's stop there for now. I think that's already a lot of policy gradients for one day. And then, yeah, have a good weekend. Feel free to ask any more questions about like the project or homework assignment on Discord. All right. Take care, everybody.